Hey, Dr. Clark back at you again with another stats video. This time we're looking at an example problem for least squares linear regression. Let's jump into it. Example 10.3, predicting temperature from cricket chirping. So this is kind of an interesting idea. If you listen to the crickets and you kind of checked out how many chirps per minute they're making, could you use that information to predict what temperature it is outside? Well, you might be surprised. So here's the data. So what they did was they spent a whole night or maybe over a couple days. They marked down the temperature in Fahrenheit at different times, and then they marked down how many chirps per minute a cricket was making. So was it going chirp, 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 or chirp, chirp, chirp? They counted the chirps per minute, counted the temperature, waited till it was a different temperature, made another measurement, different temperature, different measurement. So again, we've got two quantitative variables. For each given point in time, when they took an observation, they measured the temperature and the chirps per minute. And so that gives you, two quantitative variables. You can plot that data on a scatter plot, right? So here's a point in time, right? There's a chirp per minute and a temperature. And what we're doing is we're going to say, hey, if we could count up how many chirps per minute the crickets are making, could we get information about what temperature it is outside? And it turns out there is what looks like a linear relationship here. Of course, it's not a perfect linear relationship, but it does, the more the crickets are chirping, the higher we would expect the temperature to be. And so we've got a positive linear relationship here. It's going up, so we got a positive correlation. I don't know what it would be exactly, but maybe 0.9. Looks fairly strong. Okay. So the relationship appears roughly linear. Here's the line that goes through it. That's the least squares linear regression right there. The applet will generate that for you. I can show you how to get the applet to generate that for you. So you're going to go to correlation regression. You would paste in the data like so. I've got it pasted in here. That makes the data go, and if you click show regression line, boom, there's your regression line, and it tells you the predicted temperature is 37.14 plus 0.2414 times the number of chirps. So this is your x, this is your slope, that's your y-intercept, and that's your y-hat. Okay. Oh, and we can figure out what the correlation coefficient is, 0.96. Ooh, it's quite strong, actually, stronger than I thought. So there you go. Okay, back to the slides here. So the regression equation, again, this is sort of, you can imagine that y-intercept would have to be way over here at 0. That's that 37 we saw. And then, as we go over 1 minute, how much does the temperature, or over 1 chirp per minute, how much does the temperature go up? So it turns out that is the regression line. Y hat equals 37.14 plus 2414x. The predicted temperature is 37.14 plus 0.24 times the number of chirps per minute. This is putting it in context. The predicted temperature is the y-intercept plus the slope times the description of the variable in context, the number of chirps per minute. See, this is sort of mathematical, but this is showing me that this is real data that has meaning and you can interpret it. And then you can say, well, what is the predicted temperature if it was 100 chirps per minute? Well, you could plug in 100 for x, multiply that out, and you get 61. You would say, it's probably about 61 degrees outside. So could you predict temperature using cricket chirps? Turns out you could. And because the regression line is fairly, tucks in with the data pretty good, you might expect that prediction to be fairly accurate, which is pretty fascinating. The slope is 0.2414. That means that if you went from 100 to 101, then you'd expect the temperature to be going up by 0.24 degrees, right? For each extra chirp per minute, we expect the temperature to increase by 0.24. It's increasing because that slope is positive. So the slope is the predicted change in response variable for every 1 unit change in the explanatory variable. In this case, again, the slope and the correlation are both positive. They're not the same number, but they are both positive. The y-intercept is 37.142. I guess that would be saying that if the crickets were chirping 0 times per minute, we would expect it to be 37 degrees outside. Now, is that going to be accurate? Probably not, because the data's all over here, and so if we predicted way over here, that's extrapolating. Now, what if it was 50 chirps per minute? Well, that would also be extrapolating, but might be more accurate than extrapolating at 0. But if it was, say, 120 chirps per minute, you might get the temperature fairly accurate using our model. Okay. And so when would you interpolate? You know, between 70 and 150, that's when the data is, so that would be the reasonable range to do prediction. Finally, the coefficient of determination, because the R value was 0.96, R squared would be 0.962 squared, which is 0.925. So that's telling us that 92% of the variation in temperature is explained by the variation in, or by the knowing the cricket chirping, essentially. So the temperature for these data points, there's all different temperatures, right? But 92% of the information about what temperature it is explained by knowing how many chirps per minute the crickets are making. So that's telling you that cricket chirping accounts for a lot of knowing what temperature is. In fact, 92% of that information is accounted for. So is it perfect? No. I mean, here's two, you know, all three of these crickets are chirping at the same rate, but there was 3 different temperatures. So it's not 100% perfect, but it does account for and explain a lot of the variation in Y. Okay, your exploration that you're going to be working at is predicting height from footprints. So if you could see a footprint in the dirt or something, could you predict how tall the person was based on that? Well, what you're going to do is you're going to jump over to your applet, click on correlation regression. When you do that, I think they've already got that footprint height data locked in for you, but of course the data sets are always down here. 10.3 foot height right there. You can paste that in. And then, show regression line. It will give you the regression line. It will give you the regression equation, gives you the correlation, gives you the R squared value. And then you're off to the races in terms of doing your exploration 10.3. So I hope that's good enough for you. If you have questions, of course, you can give me a buzz, and we'll see you next time.